you've learned quite a bit about scientific workflows and scientific workloads and how to leverage hundreds or thousands of computers. When you're doing that, though, you have to understand network and data locality considerations if you're going to get optimal performance. We want you to see that 1,000 times speed up when you use 1,000 cores or 1,000 servers. To do that, we're going to talk to you today about network, data, and where the bottlenecks might be when you're trying to take your science and distribute it out over a larger resource, especially when your science is data intensive. So let's go through a couple of examples. First, we'll start with a scientist. We have our scientist, and most scientists are comfortable with their research environment, their research computing environment, whether that be their laptop or a desktop within their lab. Within that environment, they understand that they can move data onto the hard drive of the computer. They can do that with USB flash drive or an external hard drive, or they can go out over the network using Wi-Fi or using a cable on their LAN network. And that's how they're used to moving data in and out. They understand how long that should take, and they're comfortable with that when they've been moving data on and off their computer for various reasons. But now we're going to go into a larger distributed system. When we go into that larger distributed system, we have to think about network considerations. So what's out there that we might want to get from a distributed system? Well, first, the data may not be local to us. Think about if you wanted to go out to a genome database. That database may have a gigabyte of data you need, a terabyte of data you need, or 1,000 terabytes. Maybe it has a petabyte of data you need. And each one of these, whether you're at a gigabyte, 1,000 gigabytes, a petabyte, those all require different demands upon the network that you're going to use. And it's important to understand those. A gigabyte's about the size when you're used to downloading a video. But when you get to 1,000 gigabytes, things behave a little differently in the network environment. That's another example. You've been learning about high performance and high throughput computing. So what does that look like? So you've got tens, hundreds, maybe thousands of compute systems in the clusters. And once we've got our cluster of systems, they may be interconnected. So they may be connected one to another or in some complex network between the machines themselves. Then you need to connect to those networks, okay? So that we can get over to that HPC for our high performance computing environment, or HTC, that high throughput computing environment. What else? Well, let's think about what if you're collaborating with folks with real-time data? Real-time data coming in from sensors or coming in from folks in the field, maybe taking surveys. Maybe you've got a large number of folks that are taking surveys even dynamically. They're not actively taking surveys themselves, but they are actively in as much as there's a sensor on their phone collecting that data. So we've got sensors, we've got surveys, so we've got a lot of information out there that we might want to get access to. So we'll talk about dynamic sensor and survey data that we might want to be able to get access to, okay? And then we'll talk about one other example to get us started here today. What if you are partnering with an experimentalist, or your lab also has an experimental component? You've got experimental equipment that you need to consider moving data on and off of that you're going to compute upon. And so you have an experimental facility. Could be a microscope, could be a high energy physics facility. We'll go with a traditional picture of a microscope here. You can make this microscope as powerful as you want in your mind, generate lots and lots of data. But we've got to move data in and out of that experimental facility. All right, so these are 4 examples where you might have some data-intensive scientific computing to do. You might be doing a workflow here. You might be doing a workflow across multiple different platforms. All right, so what do we move and how do we move that data? Let's think about a couple of those considerations. Talk about bandwidth first. You might have a high bandwidth capability pipe. So if this is high bandwidth, and bandwidth is the amount of data we can move in a unit time. Typically, we think of this in megabits per second or gigabytes per second. You might have high bandwidth. You might have a very low bandwidth pipe. Okay. And that's going to change our expectation of what we can move and how we move it. Right? If I can move at high bandwidth, terabytes of data or gigabytes of data, we need to understand how many days or how many seconds it's going to take to do that. Whether you're personally waiting on that data transfer or whether you've got a system out in the HPC facility that's just waiting to get access to that data over the network. That's important. What else do we think about? Well, we have to think about how far away or how many hops a piece of data has to make in that network. You can think of these as stopping points for that data where it keeps getting switched or routed and it keeps getting moved around inside the network. All right, so we might have a complex multi-hop route. And that complex multi-hop route is going to introduce something called latency. And that higher latency, which is the time from one to the other. So if I was trying to get an acknowledgement on a package arriving or a packet arriving, I have to wait on that latency. So high latency can be very bad. So if this is very long, high latency can be introduced, which is not good. We don't like high latency in our networks. So we know we have different types of bandwidth. We have to think about the latency that might be in our network. What else do we think about? We talked about sensors and surveys, people. You can imagine some of this data could be sensitive. So if we're going to do a network analysis, we also have to understand that network is also a tool where they often apply security. Okay, there are tools within the network to apply security, and one of those tools, in a very generic use of the word, is a firewall. And so you need to understand that there are often firewalls in your network for very good reasons to provide security for your data or someone else's data, and that those firewalls can block what sometimes seem arbitrary, an IP address, your specific ID, a specific port, but they're there for specific reasons, and you should talk with the experts in your research networking community at your institution to understand what firewalls might be in place. And then last, for an example here, for your experimental facility, we need to talk about quality of service in the network so that at specific times, if I have a switch in my building and it just happens to get overloaded, if I get a saturated switch, and I don't have any specific quality of service guarantee, a very expensive experiment that maybe only happens for a few hours just happens to occur at the same time everyone else in the building wants to use the network, and we don't actually capture the data and we lose the data from that experiment because we don't have control over the quality of service that we can expect for that particular network. So all of these parts are something that we need to think about, and there's more if we're going to optimize. One last item that's becoming more important as our scientists collaborate nationally, internationally, and between domains is moving that data not back and forth to the scientist himself or herself, but how do we move data between those external resources? It may not make sense to move a petabyte back to the scientist only for the scientist to try to upload it into a compute facility. Can we connect those two facilities directly? Can we move some of this Internet of Things sensor data into our HPC facility and vice versa to inform those particular systems without bringing it all back to a central bottleneck point? So trying to figure out how the network works, not just from a central hub, which is the scientist, but between all those resources that the scientist has access to. If we can optimize these pieces in our workflow and in our workload, we can really accelerate that science, help reduce your frustrations, and accelerate your time to discovery.